Energy band diagrams. Bands are formed in semiconductors or in any metals, any materials, any solids. So what is the concept of energy band? Stay tuned and watch the video till the end for the clarification of the concept. Here we go. So here I'll explain the formation of energy band in semiconductors first. So I'll take an example of a silicon, which is widely used semiconductor, whose atomic number is 14. So if you write the electronic configuration of silicon, this will be 1s2, 2s2, 2p6, 3s2, 3p2. So 3s2, 3p2, that forms the outermost shells, and the electrons in 3s2 orbital and p orbital, 3p orbital, they are called the valence electrons. Alright, that we understand. Now let us try to understand this, the energy band, how it forms in the material silicon when it crystallizes, when all the atoms comes together to form a crystallized solid structure. Alright, so here we go. So I have taken some pictures here. This is the atom, one silicon atom here, and we have a nucleus, positive charge. I have just drawn the outermost orbit shells. So this is 3s shell and this is 3p, and I've taken two atoms. This is 3s, 3p. Alright, so there are two electrons in 3s shell, two electrons, and the 3p orbital is having slightly higher energy than that of s shell. This energy difference. So higher energy means it is slightly far from the nucleus. So I just taken the Bohr model of this. Of course, the p orbital will have a dumbbell shape and all those things. To simplify, I've just drawn like this. And yeah. There are 6 states in p orbital. That means 6 electrons can occupy in p and 2 electrons in s orbital. That you know, right? So but here, for the case of silicon, p is only filled with 2 electrons. So there are 6 states at this energy level, closely spaced, but only 2 electrons occupied 2 states. 4 states are unfilled in this. And there are 2 states in 3s orbital energy level, and both the states are filled with the respective electrons. Alright. So this is a condition for an isolated atom, or when we take 2 atoms, when the difference, the spacing between the atoms is very far, the interatomic spacing is very far. In that case, it will be like this. So I'm just drawing a diagram here. So here in the x-axis, this interatomic spacing, that means the distance between the 2 nuclei of the atoms, nearby atoms. So let us say I have just taken 2 atoms here, and these 2 atoms are, say, very far. The distance is very far, I suppose. And in the y-axis, I have taken energy of the electrons, energy levels. So 2 things are there here: the energy states and the electrons which are occupying those energy states. So in the p orbital, there are it is slightly higher energy than the s. So I'm just drawing when the interatomic space is very far, you can treat this as an isolated atom, so that won't change. So this is occupying, this is a p energy level, and there are how many states? 6 states, 6 energy states there. and how many electrons? 2 electrons. 2 electrons. Okay. And in the s orbital, the energy level is this. And here, how many states are there? 2 states and 2 electrons are filled. Okay, so in this all states are filled. So now the interatomic space is large there. As you keep on bringing them close together, the atoms are coming close. What will happen? When they're coming close, due to the interatomic interaction, the energy levels will be splitting. Well, as you bring closer, the energy levels will be splitting like this and they form a band like this. So at a particular distance between the atoms, the silicon material will be crystallized. It becomes solid. So that is called the crystallized state. So that is interatomic space will be fixed at that point of time. At a particular temperature, it becomes crystallized, it becomes solidified. Okay, so it will stay there. So at that particular point, this is your crystallized state. State of silicon. Okay, now we can see what happens here. When the distance is very far between the atoms, there are 6 states in the p and 2 electrons only. There are 2 states and 2 electrons in the s. And when they come closer here, what happens? They started spreading. So all the filled electrons, all the electrons will come to this below level, and again the levels of energies, they will not occupy at a particular level, but it forms a band over there, and all the 4 electrons will be coming to this below level. And at the upper, again there are allowed states but no electrons. There will be 4 states here and 0 electrons, no electrons. And here 4 states, 4 energy states, energy levels, allowed energy levels. Okay, and then 4 electrons. So all the 4 electrons, 2 electrons from p also comes here. There is no p and s here. So it forms a band of energies which are filled with electrons. Another band of energy levels which are empty states. There are 4 states for one atom. So if there are n number of atoms, there will be 4 n empty states which are there in particular energy band. So that is called the conduction band. This is called the conduction band. And below this is called the valence band, which is all 4 n states, energy states will be there, which are already filled with electrons. So what happens when they come closer to one another? So what is happening to these electrons? So all the 4 electrons here, actually they are forming a band of energies, different levels actually, like this, the conduction band. And also here, sorry, in the valence band and in the conduction band again, different levels. Alright, so I'm not drawing the full circles. It forms a full circle. So now the electrons are now arranging themselves. All the 4 electrons will come to different levels. Assuming that it is having the full circle, just see the full circle is all 4 electrons have come to the valence energy band, because there are 4 energy states are there, 4 allowed states are there, which are closely spaced. Of course, I have drawn as slightly away from each other. And again there are energy states somewhat above this. At a particular level there are 4 states for each atom. There will be 4 n states. And now if you see, there is a gap between these two, and there is a gap. So this is a gap between these. So if you draw a full circle here, okay, and there's a gap here, so again draw a full circle. And in between this gap, no electron can occupy the energy. So these energy levels are not allowed for the electrons to occupy. So that is why these energy levels are called forbidden energy levels. Okay, so the electrons either can, when they're excited, they can just jump and go and occupy any of these energy levels, or they'll come back. When they're coming to the lower energy, they'll come back here. So they cannot occupy any of the space here. So this is called the forbidden gap. This is called the forbidden energy gap. So if you see this, so there are so many atoms. Actually, I've taken only 2 atoms. There will be so many number of atoms. When they come together, interatomic space is fixed. For silicon, it is 5.43 angstrom. Interatomic spacing, this one is 5.43 angstrom. So when the spacing between the 2 atoms, adjacent atoms, is 5.43 angstroms, it becomes solidified, it becomes crystallized. It will be like that only. Okay, so there will be so many number of atoms. So when you see the if you see, take a slab of silicon like this, then along the length of this, it will have an energy distribution, top level and bottom, and this is called the conduction band, this is called valence band. Okay, so here in this diagram it is conduction band, and this is valence band energy level. So it becomes constant throughout the slab of the material. The difference between these two, EC minus EV, is called the energy band gap, EG. So this is energy band gap. For silicon, it is 1.2 electron volt. Okay, so for silicon it is 1.2 electron volt. So now we'll see for other materials. For metals, there is no forbidden gap. They'll merge. The interatomic space is in such a way that, for example, if you take aluminum will settle at some interatomic spacing. So there both the it will settle somewhere here. So for example, it will settle somewhere here. Then both conduction band and valence band will merge together, and there are plenty of electrons available in the conduction band itself for the material to connect. So it will act as a good conductor of electricity, aluminum. Similarly, if you take insulators, silicon dioxide or anything, so the energy band gap is very large. The interatomic interaction is in such a way that the energy band gap, EG, will be very large. For example, I'll give you some figures here. For metals, the energy band gap is 0, no band gap. For semiconductors, band gap is moderate. It is around, say, for germanium it is 0.7 electron volts, for silicon it is 1.2 electron volts. For insulators, for example, silicon dioxide is an insulator. So for the energy gap for this is around 11 electron volts. So when it is 11 electron volts, then it acts as an insulator. Alright, so only those electrons we'll see the carrier concentrations, and what is the concept of Fermi level, and what is the concept of, how to calculate the carrier concentrations, electrons and holes, and the probability of occupation of the states. That we'll see in next video. So this is a concept of energy band diagram in materials.